All right, 3. Now we're going into trigonometric functions. So sine, sine, cosine, tangent. So these are also known as transcendental functions, the list of functions that we're studying now. So it's polynomials, exponentials, and now we're going to trigonometric. And the reason why the book is called Early Transcendentals is because of what we're doing right now, where we quickly introduce derivative and then we go straight to how to derive transcendental functions. Right? Polynomials are algebraic functions, actually, right? And the other ones, exponentials and trigonometric, they're transcendental. So this is something that allows us to use a lot of the more complicated, interesting applications of calculus. So this is why most people nowadays go early transcendentals in the sequence of the course. But sometimes you'll see books where those things we're seeing now are at the end, just so you're prepared. Stewart's is the most used book with early transcendentals, so that's the most common approach. So the goal here is to try and see what is the derivative of the sine function, and then the cosine, the tangent, and so on. Let's start with the f of x equals sine. Let's remember that whenever we write this, this is the radian measure. So we're not plugging in x equals 30 degrees. We're not doing that. We're doing x equals pi over 6. So all of your math 142 is going to be useful and play a huge role in this here. Okay? Remember that they're all continuous. All trig functions are continuous. So this is an important fact for us to use from now on at every point of their domain. So for functions with weird domains, you have to be careful. So for example, sine is continuous, cosine is continuous because the domain's all real numbers. But if you go, for example, cosecant, say, which is 1 over sine x, you have to be careful. This is continuous everywhere except possibly where it's undefined, which is where sine equals 0. So you gotta look at the unit circle, add pi over multiples of 2 pi, and so on. So let's keep going with this. So let's think about what's our expectation for the derivative of sine. So first thing you've got to notice is that graphically we know that the derivative is the slope of the tangent line. And looking at the graph of sine, which is the blue one, there are clear points where the derivative is 0, which is the points where the slope of the line is 0 because the line is horizontal. Okay, so when the tangent line is horizontal, the differential or the derivative equals 0. So this is what we do. Look at the bottom graph and we put these points here. That's the first thing that we do. Okay, so you get a list of certain numbers, right? A pi over 2, for example. A pi over 2, and then pi later, right? You get 3 pi over 2, so you get 0. And this is already hinting towards one known function, right? You also have like these other points where, okay, this is probably the maximum value here because that's where the line is the most steep, right? Or the steepest. And here it's the minimum because that's probably where it's the least steep, or like with negative slope. So this is hinting towards a function that's known to all of us. This here is the graph, and I'll put in red. This is the graph of cosine. And in fact, it is true that the derivative of sine is cosine. We're just going to have to work a little harder to prove that. So I'll just walk you through a little bit of the proof. Here's the idea, okay? You write the definition of derivative, first of all, and then with sine, you got to do this, sine of x plus h minus sine of x over h. And here you're using the sum formula, and that's math 142 as well. So we're doing the sum formula. I think in the Blitzer book, it's probably section 5.2 or something. Basically, we're saying sine of a plus b equal to sine a cosine b plus sine b cosine a, and this is what we're doing here. A is x and b is h. Okay, so we're using the sum formula on this one step here to open this up into this whole thing. Okay? And now we group these things, and we're grouping them on purpose because now we can factor the sines. So here's where it ends up. And here we get a very cool, crystal clear idea of what needs to happen. The cool thing as well is that because the limit is when h goes to 0, x is treated as a constant. It doesn't change. So the things that depend on x only, not on h, can come out of the limit. And you end up with these 4 limits, these 2 of which are very easy to compute. Don't have to be understanding 100% of the calculation to get an idea. If you're interested in this, just stop and think about it and actually follow along while you write it if you're interested in that. The idea though, is that these limits are easy. So this is easy and this is easy. So you end up with sine x times a certain limit plus cosine x times another limit. And this one I'll write, because this one is what we talked about this in one of the classes, one of the initial classes. This is the fundamental trigonometric limit. This limit equals 1. We investigated this using a table and plugging points in. I don't know exactly which lecture it was in. You can remind yourself and look for it. I think it was very close to the beginning of the quarter. But we can sort of try and prove this using geometry. It's very complicated. They use like circles, sectors, and then I don't like these proofs that the book does because it looks very sketchy, because in the proof you use a lot of things that are difficult to believe, right? A proof is supposed to be a sequence of logical steps using only things that are easy to believe, right? Until you reach a point where you conclude that what you wanted is true, right? So you do a lot of steps, use things that are easy to believe to conclude something that was harder to believe is true, right? That's the goal of a proof. And in the book, they don't do a lot of that. The idea, again, I'll go back to this and I'll prove this once we go to what's called the L'Hopital's rule. Prove using L'Hopital's rule. So L'Hopital. French person, there's an accent on O. It's a French mathematician. Most people say hospital's rule or L'Hopital rule. The L sometimes is omitted. Most people pronounce it wrong. Or add an S after the O. Hospital rule or something. L'Hopital's rule is what I'll call it. And once we get there, we're going to revisit a lot of this. And the idea for the second limit, and that one, so this is the one that I was talking about, right? Yeah, this is very important. Very, very, very important limit. We're going to see it later. I'll put it in blue so that you remember that it's an important limit that you use to prove other ones, but we're going to prove it later. And we're going to see a use of this because this guy, and that's the cool thing about this, which is the other limit that's left, right? This is going to be, you can multiply this by so the conjugate basically is what we're doing, right? So I'm changing the sign of this guy here into a plus, and this is a 1, so it doesn't change the result. And then you end up with, so this is the difference of squares. You're going to notice that a lot of things that you took for granted in Math 141 and 142, or that, rather, things that gave you trouble in Math 141 and 142 are now expected to be easy. So we're expected to be able to quickly see that this is cosine squared theta on the top minus 1 squared, because it's the difference of squares. So I'll eventually stop mentioning what I'm using, or just quickly say a difference of squares and stop writing it down to save time, but just be prepared. Bottom is this. So now you end up with, let me see if I can squeeze the final end of the proof here. Remember, right? As theta goes to 0, cosine is 1 minus sine squared minus 1. So this is what I wanted to make happen. This is cosine theta plus 1. And the advantage now is that I have two sines at the top. One is negative, so that's minus sine theta over theta, and that's the unit. That's the one that goes to 1, right? That's the fundamental trig limit. Minus 1, right, because of the minus sign, and that's times sine over cosine theta plus 1. As theta goes to 0, remember that's what's going on, right? This is going to 0, and this is going to 2. So 1, that's what this is. So this is minus 1 times 0 over 2. So that's 0. There's no issue with 0 in the denominator once you deal with this one, right? Once you deal with the fundamental trig limit, which is how I use it most of the time. Well, why did I do all these calculations? If I go back to the original thing that I had found, this is sine x, this is 0, I just calculated it, this is cosine x, and this is 1. So at the end, you have this whole thing equals 0 because it's sine times 0. Cosine times 1 is just cosine. So the answer is cosine. The final is cosine, right? Which is what they're doing on this slide right here. So this proves what we expected, right? The derivative of sine equals cosine. We add this to our table of known derivatives so that we don't have to go through this whole process of calculating a limit again. And now you understand the importance of memorizing certain things. Okay. One thing that's also important, and you're going to see this later, is that the derivative of cosine, by graphing and following a similar process, you can show derivative of cosine equals minus sine. So this one gives you a negative sign out here. Okay. Well, we're going to see that later. I'll just point you through it. I'm not going to actually go through the proof again. But let's do an application because that's actually how we do most of this. So I can do y prime. I could have written dy dx if I wanted to, right, using Leibniz notation. Most of the time I'll choose one, whichever one makes sense for me at the moment. You just have to do the same. You can use the same one all the time, but you have to be able to understand both notations. So y prime will be d dx. Changing on purpose. So this will be product rule d dx x squared times sine x plus x squared d dx sine x. So that's power rule 2x times sine x squared, and then the derivative of sine is cosine, which is what we just found. So just maybe, I'm not going to rewrite, just erase this little multiplication symbol, box this. There's no way to further simplify this. Take a second to convince yourself of why that is. You have a power of 1 and a power of 2 here. Can't combine these. You have sine and cosine. Can't combine this. If they were sine squared, cosine squared, maybe you could. Take a second to convince yourself if that's the case. Now, like I said before, this is another known one, an important one. This is something that's worth memorizing. And after this, right, if you have the quotient rule memorized from the previous video, you don't have to memorize this one to memorize the tangent, because tangent is sine divided by cosine, right? So you can use the quotient rule, right? And they have it here. Let me actually write it here so that you see step by step. So you're doing d dx of sine x over cosine x. So then you have, let me actually write prime, right? Then it's faster to write. To have sine x prime cosine x minus sine x cosine x prime. All that divided by cosine squared of x. Right? So that's derivative of sine is cosine, so that's cosine squared x. Derivative of cosine is minus sine, right? So this becomes a plus. So that's plus sine squared x divided by cosine squared x. So that's a 1 on the top, right? So then you get a 1 divided by cosine squared, which is the secant squared. So basically they're telling you the derivative of tangent equals secant squared. This is not worth memorizing. So I'll say don't memorize. So I'm not going to write it out. I'll actually say it. Don't make an effort to memorize. Don't sit down and keep reading the table until you memorize it. You will memorize it based on the number of problems we're going to solve together, and as you go through the calculus sequence as well. But this is not worth your time memorizing. It's worth your time remembering this proof right here in blue, right? Which is the same on this slide. And memorizing sine and cosine as well, the quotient rule and things like that, because those produce the rest. So again, our table for secant, cosecant, tangent, cotangent, like I said before, these two are worth memorizing. These two are worth memorizing. And then you add the quotient rule. Good exercise for you to do right now, if you're interested, to use the quotient rule and find all of the other ones, right? All the other 3 rules. Most of the time, not worth memorizing. Once you get to calculus, to integral calculus, where you're anti-deriving things, we're going to talk a little bit about that at the end of the quarter. Memorizing these is a little bit more useful, but not right now. So here's a couple of uses for derivatives of trigonometric functions. Whenever you have periodic phenomena, things that repeat over time, trigonometric functions are very useful. And you have a couple of examples. You have like vibrations, waves, elastic motions. There's something called simple harmonic motion that we talked about in Math 142 if you took it with me. And the idea of simple harmonic motion is that you have an equation like this one. And you see the equation, right, as being as a function of time, and using cosines, for example, when t equals 0, so f of 0, so that's an example, when t equals 0, this is cosine of 0 equals 1, so s equals 4, so that means the distance is 4, right, so this is where it starts, and then when t equals, I don't know, pi or something, then this is changing, the height is changing. If you graph the height, you get a graph of a cosine function dilated by 4, right? Stretched out by 4 in the vertical, okay? There will be negative, there will be negative height. So that means, oh, let me correct the graph here actually, because they're saying this is the rest position. So this is the rest position. So this guy's 4. And when they give me negative height, that means like the box is on the other direction from the mass, in the other direction from the rest position. So this will be like a negative s. Okay? It's an example of negative s. But okay, how does that help me? If they want to know velocity, acceleration, let's try and look at it. The velocity v of t is the derivative of s of t. So it's the derivative of 4 cosine t. So it's the derivative of this. The derivative, so 4 comes out, right? Linearity of derivative. I'll stop doing this extra step eventually. I'll just go straight to the next one at some point. But then the derivative of cosine is minus sine, so that's minus 4 sine t. Cool. And the acceleration is just deriving it again. So a of t is v prime of t. The acceleration is how velocity changes, the rate of change of velocity, so it's its derivative. So that's minus 4 cosine t by following a similar process. Okay, how does that help me, right? we can tell exactly the points in time in which v of t equals 0. So if you go v of t equals 0, you have minus 4 sine t equals 0. So this is the end of the problem, right? I'm just expanding a little bit now. So the velocity is only 0 when sine equals 0. And sine equals 0, if you go back to the unit circle, sine is the y-coordinate. Sine equals 0 at the beginning, here, and at pi. Okay, and then adding multiples of 2 pi to these. Whenever t equals pi, for example, when t equals pi seconds, then sine equals 0, so velocity equals 0, so that means the trajectory is changing directions. It was positive, it's becoming negative, or it was negative, it's becoming positive. At that instant of time, the mass has stopped, right? So if we were to draw it, right, let's say it starts here, and then for some reason it goes down like this, and then at this moment it starts going back up. This is t equals pi seconds. Okay, this is the moment where velocity is 0. When it stops going down and goes back up, and it's going to happen again. It stops going up, and starts going back down. So that's one of the very important uses. Take a second, stop, and think about this. And that's one of the very important uses of derivatives, finding the maximum of a certain value. So we're finding the maximum distance between this, which is actually exactly what the last slide says. The speed, which is the absolute value of velocity, is 4 absolute value sine t, which is max when sine t equals 1. So we have max speed is 4. I think centimeters per second. Could be wrong on that. Let me see. Centimeters per second. Doesn't say the unit of time, but I'll just leave it as seconds. So that's the max speed of the mass in the simple harmonic motion, and the min would be 0, right, which is when sine equals 0, which is possible. Okay, so we found the max speed of this thing by analyzing the equation of its position and finding its derivative. So that's a very important, very cool thing that we're able to do. We're going to see how we use this later on in the class. As the class progresses, take a second, understand what I did, understand what we did together, and thank you for watching that.